And just as a quick recap of last lesson, so we went over backprop in a pretty short lecture, and then we did it by hand with the worksheet. And another feedback that I got about that worksheet was there was obviously a lot of symbols going on. You saw something like this, obviously not this exactly, but you see a lot of these symbols. You see a lowercase delta, you see Z's, W's, F's and these apostrophes and transposes and all this stuff. And it could be quite overwhelming. So that was a good feedback. We'll probably make an edit to that backprop worksheet to have like some sort of legend or maybe just constant reminders of what each of these terms means. But then again, do remember that, you don't necessarily have to be like, this stuff like the back of your hand, right? Like this is just a theory. Obviously, you want to know this stuff really well if you're going to take like an intro to AI course sometime soon or be tested on this stuff. But, in practice, when we're actually writing a model.fit, like we don't really worry about all this stuff going on in the background. What is important to know is the high level math, right? So I don't know if any of you guys read the supplemental reading from last lesson, but Andre Karpathy, he's the director of AI at Tesla. He wrote this article that was talking about, backprop is what we call a leaky abstraction, and all that means is that Keras and all these great libraries, they try to abstract it away from us and make us not have to worry about the calculus and all that. But at the end of the day, you kind of do need to worry about it because if something goes wrong, you need to know what's going on under the hood to understand why it's going wrong. And just as an example of that, in that article that Andre wrote, he talked about vanishing gradients. So for those of you who are not familiar, it's just this concept of you see all these terms. So, delta 5, that's the error from the last layer of the network. And then you work back to delta 4, the fourth layer, the third, second, all the way down to the input layer. And when you get down to the input layer, you see the chain rule leads to you just multiplying a bunch of terms together. And well, imagine that, all of these terms are really small, like 0.1 or 0.01. When you multiply them all together, you get this tiny, tiny, tiny number, which could even round off to 0. And so that's what we call a vanishing gradient. And that's a problem. And so this graph, what it's shown in blue in both of these graphs is the original function. We've seen these before, sigmoid and ReLU. But in red and in green, we see the derivatives. And so if you look at the derivatives of the sigmoid graph, you see that outside of that range of -2 to 2, it quickly approaches 0. So if you have gradients outside that range, you multiply and you have them and they're being back propagated every single layer, you're going to have this problem of vanishing gradients. And in that same article, Andre was talking about the problem with ReLU. It's not vanishing gradients per se, but it's a similar problem, which is that you see if the input to ReLU is below 0, so if the weight is negative, the derivative is 0. And remember that the change in the weights is based off the derivative. So if the derivative is 0, all those terms cancel out to 0. What you have is called a dead neuron. You just, Andre really calls it like brain damage, because you've just killed that neuron. You've turned it off completely. It's not going to update. It's not going to fire. So that's another problem we have to worry about with regards to ReLU. So before I move on, does everybody understand, or I guess, is there any confusion regarding vanishing gradients and why this problem arises?
Thank you for talking about this again.
Sure, of course. So I'll take that as a no on the questions, and we'll continue on to convolutional neural networks. That's the main focus for today. And so here's just a bit of a motivation on the problem statement. What is the point? What are we really trying to tackle? So we worked with the MNIST data set before, and as you guys probably have memorized these numbers by now. We've talked about them so much. 28 by 28 pixel images means that the input layer is 784. And that's not too big of a number. That's very easily handleable. Also, the images are black and white. That's also quite nice that it's just like you can represent one pixel with one number, which is great. So even if you had a first hidden layer of 10 neurons, you do a little math here. The number of parameters in the first layer is 784 plus 1 all times 10. That's 7,850 parameters. Can someone really quickly remind me, where did this +1 sneak, like how did that sneak into this? Where is that coming from?
Is the bias term.
Yeah, exactly. Armand got it. The +1 is, it's not connected to the input layer, but it's just another neuron. Because remember, the bias doesn't have a weight, so there's no reason to have a connection there. So yeah, it's the bias. But yeah, 7,850, that's no problem, right? That's pretty easy. But if you wanted to classify a slightly bigger image, like 256 by 256, and it was RGB, it had color values. Well, each pixel then needs to have 3 values, one for each channel, red, green, and blue. And 256 by 256, I mean, that's almost a 100x increase. Yeah, that's almost an 100x increase. And that's already 65,000 in the input layer times 3 per channel. So if you had that same exact hidden layer of just 10 units, you do the math, all of a sudden you have 1.9 million parameters. And that's a significant jump from 7,800 to, you know, nearly 2 million, right? So that's really the problem statement here, is that, you know, there's way too many parameters. It's quickly becoming computationally expensive. And so the solution is to downsize it. And you know what? It would be nice if, while we're downsizing it, kind of like a 2-for-1, we could extract some salient features. We could extract some sort of valuable information from these images. And so that's where convolution and pooling comes into play. So at this point, what I'm going to do is just kind of do like a quick run through of these slides. And I'm just gonna like, this is kind of aimed towards like the advanced group, because Raj has a separate, slide deck for the advanced group. You guys are going to be learning about autoencoders and stuff like that. So this is just going to be a quick recap. And if anybody from the advanced group or the intermediate group, if you guys feel like, okay, I'm good on all this stuff, then you can join Raj. And if you feel like, oh, maybe it'll be better if I review this stuff, then you can stay here. But what we're going to go over is, you know, what is a convolution? What is a kernel? You know, what is it doing? A nice Grant Sanderson visualization. You know, the Sobel kernel gives some intuition behind why that works and why that does edge detection. You know, how they stack, pooling. So you know what the point of that is. And that's kind of it. Yeah, and then just like the overall architecture, and then that's pretty much it. So yeah, that's what we're going to be talking about. And if you feel like, you know, you might want to stay for this one, then definitely hang around. But if not, at this point, the advanced group can split off and join Raj. Okay, so let's get into it. So yeah, first of all, what is a convolution? So it's very simple. All it is you have a kernel, and a kernel is just like an n by n matrix of numbers. And these numbers are applying some sort of transformation to the image. And so all it is, what you're seeing in this GIF here is that this kernel is a 3x3 kernel, and it has 1s on the diagonals and 0s everywhere else. And what it means to convolve, or to run a convolution over this image, it just means starting from the top left, placing this matrix on the top left of the image values, and taking the dot product. And the dot products, you know, once again, is just multiplying whatever numbers are on top of each other, and then adding them all up. So you see like 1 times 1, 1 times 0, and all those. You're taking all those products and adding them all up. And then you're adding them all up and you taking that final value and putting it in the convolved feature. And you'll notice something. Obviously, you can't run that 3x3 kernel over the top leftmost pixel, right? Like the top left pixel can never be in the middle of the kernel, because there's no pixels outside of that. That it's the border. So in the process of running this convolution,
Hey, can you guys hear me?
Yeah, Julie? Was that Julie, I think? Oh, wait, that was Raj, I think. Okay, all right. Continuing on. Yeah, so the border, like, the border pixels are never going to be in the middle, the center of that kernel. And so what you get is actually you're reducing the size of the image. The image starts off as a 5 by 5, but after you run the convolution over and take the sum values, you actually just end up with a 3 by 3 image. So does that make sense why the image is getting smaller? And also, is there any confusion regarding what is going on within a convolution? What exactly is happening? And I'll show another nice animation after this. Okay, so to take a look at another pretty nice animation, quick shout out, by the way. So Grant Sanderson, he's the same guy who runs 3 Blue 1 Brown, and we just, go crazy over his YouTube channel because it's just so great. He's teaching a class at MIT actually called Computational Thinking, and it's the entire thing is online, available for free, and a lot of the lectures are on YouTube. So I actually I screen recorded this from one of his lectures, converted it to a GIF, and then added it to these slides because I really liked it. And what this is showing, this is called a Gaussian blur. This kernel is called a Gaussian blur. It could be a 5 by 5 kernel, or it could be a 3 by 3 kernel. I think here it looks like a 5 by 5, but all it is it's a Gaussian a normal distribution, a bell curve. As you can see, it kind of looks like that, where the middle value has the highest number, and then the middle, the layers outward get less and less. They have lesser values. And what that does is when you're convolving over this image, what you're basically saying is, okay, I'm going to take a sort of weighted average of everything in this window, right? And I'm going to weight the middle pixel the most. And everything kind of working outside of that is going to have less and less of a weight, of emphasis on it. And then I'm going to sum that all up. And so when you sum that all up, so you're basically saying, I really only care, I'm like averaging this, I'm kind of mushing all these pixel values together and averaging them into a sort of one pixel, and making that weighted average kind of very biased towards the middle pixel. And when you run it over and you keep sliding this convolution and doing it over and over again, you see on the right here, you get this blurred effect where it's all the pixels are kind of mushed together and blurred together. But like, because we put the emphasis on that middle pixel, we still sort of get what, the main idea of the image, of what's going on. And so here's another really popular kernel, and this is called the Sobel kernel. And this is used all the time in edge detection. And this one looks just completely different than like the Gaussian blur or what we saw earlier. But I think it's really cool. I mean, look, the left is the original image, and the right is just after a symbol running the Sobel kernel. There are actually multiple Sobel kernels. They're all the same, just rotated. They're just rotations of each other, like simple 90-degree rotation. So there's 4 of them. But after you kind of stack them all together and you run them, this is what you get on the right-hand side. And I think it's pretty crazy. Because it's like, in theory, it's such a simple thing. You're just doing a bunch of multiplications by this matrix, dot products by this matrix. And then all of a sudden you get like this really clear and defined black and white image with white on all of the places that you want to find edges. And so if you're wondering like, why does this work? Actually, I'll try and give, if someone wants to volunteer and try to explain this. It kind of relates to back when we were talking about, I think it was 2 lessons ago, we were talking about like putting weights. Yeah, for hand digit classification, we're talking about putting weights. So does anyone want to try and like explain like what this specific kernel, this 1 2 1 0 0 0 -1 -2 -1, like what might this be doing? What sort of effect might it have when you run over an image? And as usual, you can just drop guesses in the chat as well, or even just like say like whatever whatever to be true. Doesn't have to be a complete answer. It could just be a guess.
I'm not sure exactly how it relates to the kernel, but I know the Sobel operator kind of thing basically looks at really drastic changes in like color or just like shade, I guess. So you can see like there's an outline around areas where there's like a high contrast, I think.
Yeah.
Yeah.
Yeah, absolutely. It looks for differences in high differences in pixel values. And how you might imagine this, a good like thought experiment that I like to do is um, think of just if the 3 by 3 image portion of the image that you're looking at was either monochromatic or like some really simple pattern like all whites and all blacks or something like that. So imagine that the top row was all white and the bottom row was all black. Okay, if that was the case, then the output of this kernel would be very, very positive, because white would have a very, very positive value and black would have like a close to 0 value. Depending on how you normalize it, it might have a negative value, but usually 0 to 1. And so you would just get this sum of a bunch of positive numbers and get a very positive value, which would be white in the final image. Whereas if it was black on the top row of this 3 by 3 fraction of the image and it was white on the bottom, then obviously it would be a very negative number, and then you would get black in the final image. So that being said, does anybody have a better idea of what this specific Sobel kernel is doing? And I'll give you guys another hint. Remember that there are 4 versions of this Sobel kernel. They are all simple 90-degree rotations of each other. So now with that hint, this is obvious, has to do something with edge detection. What edge is this looking for? And like, I guess you could say like, is it a top edge, bottom edge, left edge, or right edge? What edge, if it exists in the 3 by 3 fraction, would give the most positive result?
Oh, the top edge?
Yeah, exactly. Like Neil said, it looks at the top edge, and if you just rotated this thing 180 degrees, then that same exact kernel would look for a bottom edge. And if you stack them all together, then it's looking for all possible edges, and the final result is what you get here. So yeah, if this is like slightly confusing to you, once again, I highly recommend, this is in the supplemental reading docs in the same folder too. Check out this video. He goes much more into depth, and you see numerous examples of kernels. And yeah, it's kind of one of those things where if you try to like think about it and run thought experiments of your head of like, what actually happens with the numbers if I try like a all white image, all black image, white on top, black on top, white on left, whatever, kind of just mess around with it. And like, you'll see that you'll slowly get an intuition for what's happening. So yeah, you can stack a bunch of these filters together, just like you could do with the Sobel filter. And then what you get is a stack of filtered images, and they carry some sort of salient information regarding the image, like where are edges, where are the edges in the image. You could do the same thing to find loops, and all sorts of really, really neat things. So next is pooling, and pooling is it is not as sophisticated as convolution. As it sort of implies in the name, it is pooling together a bunch of values. But yeah, looking at these numbers, right? So looking at the orange, you have 1, 0, 4, 6, it goes down to 6. The green, you have 2, 3, 6, and 8, it goes down to 8. And etc. So could someone quickly see the pattern here? What is being pulled here? What is ending up in that final box? What is special about that element with regards to every other element of the same color?
It's the largest number.
Yeah, it's the max. Yeah. So this, because it's the largest value, this one is this is called a max pooling layer. It's a simple 2 by 2 kernel. It slides over the image, and over each 2 by 2 segment, it just takes the max value. That's literally it. And you'll notice one thing when it's sliding over. Notice how so like, let's say that it started here. We could have moved it and done this, right? We could have we could have max pooled this box here, but we didn't. We actually just did this, and then we moved all the way here, and then we moved all the way here. Like we could have done this too, all these intermediary steps, but we didn't. And the reason for that is because this is called the stride length, and the stride specifies how much you're going to move the window each time. And in this particular example, they just happen to use a stride length of 2. So instead of going from here to here and then from here to here, if that makes sense, they just skipped 2. So yeah, they use a stride length of 2 by 2, and that's why you ended up from going from a 4 by 4 image to a 2 by 2 image rather than like a 3 by 3 or something like that. But so does pooling make sense? Does everyone understand? Or like, yeah, is there any confusion regarding what pooling is doing or how it works? And so yeah, just as a kind of a recap, pooling is not as, I guess, cool as convolution. It's not as powerful as convolution because it's like it kind of implies in the name. It's just pooling that it's just a way of making the image smaller. That's all it's doing. It's just saying, like max pooling in this case is just saying, okay, I want to make this image smaller. I'm just going to take like the biggest pixel value from this neighborhood and forget about the rest. Whereas convolution, you can get some cool edge detection and things like that. So yeah, I honestly have no idea why this slide is here, so I'm going to skip it. Fully connected layers. So yeah, the filtered images that run through the convolution layers and the max pooling, they then, so all they're doing is reducing the size of the image, you know, sequence by sequence, but the convolution is getting some pretty salient information and storing some pretty helpful information from them. And then just like regular, at the very end of that pooling, the convolution and pooling, you just feed it into a regular feed forward network of however many units. And then, you know, that final, if we're doing multi-class classification, you have that final layer, which will use an activation of softmax to give output probabilities. And so this is what the overall architecture might look like. You have this input image of a car. You have a convolution, which is looking at some sort of kernel of the image, downsizing it, but also while it's downsizing it, it might, you know, detect that edge, that outer edge of the car and accentuate it and make it white and make everything else black. And then you'll run a ReLU on it. And the reason we do that, so convolution, the kernels in a convolution are back propagated just in the same way that you back propagate over the weights in a neural network. It's the same exact thing. It's just the math is a little bit different. And if you're curious about the math of back propagation on convolutions on kernels, there's actually, I posted something in the supplemental reading that you can check out. It's like, yeah, there's quite a lot of symbols and stuff going on, but yeah, for those who are curious. So you keep doing this, you just keep convoluting, and then, you know, applying ReLU and then pooling and then convoluting, and you can just do this again and again until you reduce it down. Obviously, if you reduce it too much, then you're going to end up with like a couple of pixels, which are worthless. And, you know, you've kind of just mushed all the information together. So you want to be careful with it, of course. And then you have this flatten layer. And this flatten layer, all it's doing is it's just taking a multi-dimensional array and turning it into a vector. It's just a vectorization. And then, yeah, you take that vectorized layer and feed it into a fully connected layer. And here, this would be the layer that has softmax as the activation, and you get these output probabilities for, is it a car, is it a truck, is it a van, etc. So are there any questions about the overall architecture of a CNN? Alrighty, so yeah, kind of like I mentioned earlier, we do just use back propagation on those kernel values. So when you're gonna write a CNN today, you're gonna add these conv 2D layers. It just stands for convolution, two-dimensional convolution. And you'll specify like, how big is this kernel? Is it a 3 by 3, a 5 by 5, or whatever? We back propagate on those values, like these numbers when you add a conv2D layer in a network, these are randomly initialized. And just like weights, they're randomly initialized and the error is back propagated through them. And the network asks, how can I change these kernel values to reduce the cost as fast as possible? And in the process of doing that gradient descent, the kernels learn some sort of valuable representation that learns some matrix value that's helpful, that carries information and thus reduces the loss as much as possible. So yeah, that's about it. And so some final thoughts. CNNs work best on spatially related data. That's why we have convolutions. That's why we have kernels, because quite obviously, you know they're spatially related because you're looking at neighboring pixels. You're looking at a neighboring window of pixels. So it's specific to 2D, right? That's why they're called conv2D layers. They're specific to 2 dimensions, these convolutions. And so, yeah, the neighbors matter. It's all about spatially related data. And so, yeah, if you can represent your data as an image, that's a good hint that a CNN might be the type of neural network to tackle it. And so what are some examples of this? There are a bunch. You know, Inception is a very popular model. AlexNet was, I believe, the first model, CNN model, which performed amazingly, did state of the art, and kind of revolutionized the whole game in computer vision. So a bunch of these examples, and used today. I mean, it's used everywhere. It's, you know, face detection, object detection, everything. So yeah, that's about it for now. And I'll give like one more sort of, yeah, window of time. If anybody has any questions about any of this information, go ahead and ask that now. Looks like we're just under 40 minutes. I like that. I think that's a pretty decent time. I hope that this sort of pacing and my kind of, yeah, I hope that this lecture was better. It was easier to follow for you guys, especially for the beginners, because once again, I'm not really aiming towards the advanced people here. So so yeah, with that being said, I mean, that's about it for this lecture. Hope you guys learned something, and you guys, so there's like a now 3 to 5 minute break, and then you guys can join your small groups and get started on the notebook.